Okay, lesson 10. So now we finally start to consider leading coefficients that are not just 1 and positive 1. So in lesson 7, we introduced unique factorization theorem. This told us two things. Every polynomial function can be written as the product of its factors and a leading coefficient. Every polynomial function has the same number of factors as its degree. Remember, some of those could be non-real, as we briefly touched on in the last lesson. So example 1, the graph of a third degree polynomial function p of x is shown. The graph has an integral, x-intercepts, and passes through the point 2, negative 24. So why is the equation, why can it be written in c of x times x plus 1 times x minus 3? Well, this is a direct, this follows directly from the unique factorization theorem that's written above. But basically we look at the zeros. We have a 0 of negative 1, that gives us the factor x plus 1. We have a 0 of 0, which gives us the factor x. We have a 0 of 3, which gives us the factor x minus 3, and then we have some leading coefficient. So use the point. Well, now it tells us this bit of information. Sometimes they put it in words. Sometimes we need to go read the graph to see it. But this is really telling us that this polynomial at 2 equals negative 24. So this is yet another way they have of hiding the piece of information that we need to solve for something. So we can say negative 24 equals c times 2 times 2 plus 1 times 2 minus 3. So this is c times 2 times 3 times negative 1. So this is negative 24 equals negative 6c, dividing both sides by c, by negative 6, and we get c equals 4. So now putting it back in factored form, p of x is 4 times x plus 1 times x plus 3. It also wants it in expanded form. Well, all that means is now you need to multiply this out. So it's best if if you multiply this out first, gives you a quadratic, then multiply everything by 4x. You do get 4x cubed minus 8x squared minus 12x. Okay, next one. The graph represents a polynomial function of lowest possible degree. So whenever we see that, that means any point of inflection has multiplicity 3, any point of tangency has multiplicity 2. Determine the equation in factored form. So we know our polynomial here has some leading coefficient. Sometimes they use c, sometimes they use a. Some leading coefficient. We then look at the 0. So it has a 0 of negative 2, which means it has a factor of x plus 2. There's a point of inflection there, so it's cubed. Next 0 is positive 2, which gives us the factor x minus 2, and there it passes straight through. So that must be a factor with multiplicity 1. Well, now I need to find another piece of information. I need to find a point on the graph. Here, they actually give me a y-intercept. You need to read the scale very closely, though. So this is 20, which means that we're 2 ticks down. Each tick is worth 4. So this is really negative 8. So this tells me that when x is 0, y is negative 8. So just make sure you read the scale. It doesn't always go up by 1 or down by 1. So, whoops, I forgot to substitute 0 in. So this is c times 0 plus 2 is 2. 0 minus 2 is minus 2. This gives me negative 8 equals negative 16c. Divide both sides by negative 16 and you get c equals 1/2. So in factored form, p of x is 1/2 times x plus 2 cubed times x minus 2. Example 3, determine the equation in factored form of a 4th degree polynomial function which passes through the point 1, negative 12 and is tangent to the x-axis at 2, 0 and negative 3, 0. So we're really given all we need, even though there's no graph here, but it tells us it's tangent to the x-axis at 2, 0, and it tells us it's a 4th degree function. So that tells me my two factors are x minus 2 squared and x plus 3 squared. And I need to put a leading coefficient in there. Then to solve for that leading coefficient, I need to use the information that it gives me, which is this. It passes through point 1, negative 12. So negative 12 equals c times 1 minus 2 squared times 1 plus 3 squared. This is negative 1 squared, which is 1. This is 4 squared, which is 16. So dividing both sides by 16, we get c equals negative 12 over 16, or negative 3 over 4. So putting it in factored form, they don't often ask for it in expanded form. Usually we can leave it in its factored form. Gives that. For a fourth degree polynomial, p of x passes through the point 1, 2 and has zeros negative 1, 0, 3 halves, and 2. Determine the equation of p of x in factored form using only integral linear factors. So most of this is pretty simple. So we know we have factor x plus 1, x minus 3 halves, and x minus 2. The problem is right here. Determine the equation in factored form using only integral linear factors. So this right now is not an integer. So we need to find another factor that has a 0 of 3 over 2. Well, we can kind of work backwards from this. So that's the 0. If we multiply both sides by 2, that gives us 2x. Subtract 3 from both sides. We could see that one possible factor would be 2x minus 3. Now, we can't forget our leading coefficient. And now we need to use the information to solve for the leading coefficient. So we know that p at 1 equals 2. Which gives us this. So this gives us 2 times 1 times negative 1 times negative 1, which is 2. So C must be 1. Now, if this is a multiple choice question, they're never going to give you a factor x minus 3 over 2 and then have the factor 2x minus 3. So there's usually not too much to get tripped up on here, because they will always give you kind of this option. You just need to know if the 0 is 3 over 2, that leads to a factor 2x minus 3. Example 5, a polynomial equation has the following 3 roots. Negative 2 is a root with multiplicity 1. 1/3 is a root with multiplicity 2. 1 is a root with multiplicity 3. The graph of the corresponding polynomial has a y-intercept of 2/3. Determine the equation using integral factors. Okay, so again, if we work with this 0 of 1/3, multiply both sides by 3, subtract by 1, we could find that a factor that corresponds with the 0 of 1/3 would be 3x minus 1. Putting this in factored form, we have c, that's our leading coefficient, 1 root of x, or root of negative 2, so that gives us a factor of x plus 2. Then we have our 3x minus 1 of multiplicity 2, and then 1 that has multiplicity 3. So now we can say a y-intercept of 2/3 really means we know that p at 0 equals 2/3. So 2/3 equals 0 times 2 plus negative 1 squared plus negative 1 cubed. So this is 2/3 equals negative 2c. Dividing both sides by negative 2, we get that c is negative 1/3. Putting it back into our factored form,